With the proliferation of AutoML systems, it is now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems use different approaches that explore the model search space and optimize hyperparameters in order to produce pipelines that solve a particular task. By analyzing these pipeline collections, we have the opportunity to better understand how these systems work and obtain insights that can be used to improve them. However, this is challenging due to the large number of pipelines produced and their complex structure. We propose PipelineProfiler, a tool that enables the exploration of machine learning pipelines produced by AutoML systems. Our tool consists of two main parts: Pipeline Matrix and Pipeline Comparison View. Pipeline Matrix provides an overview of the data. Pipelines are represented as rows, and primitives as columns. We show the pipeline scores, as well as an estimate of the primitive contributions as bar charts. Users can select primitives in order to explore its hyperparameters, or select pipelines in order to visualize their graph structure. Selected pipelines are summarized in the Pipeline Comparison View. PipelineProfiler is integrated with Jupyter Notebook in order to facilitate the data science workflow. As a first example, we look at the chlorine concentration dataset, where 6 AutoML systems were used to solve a time series classification problem. We load the data in a Jupyter Notebook and start the analysis with PipelineProfiler. Firstly, we see 2 pipelines with a score of 0. We remove these outliers using the subset menu. The top pipelines achieved an F1 score of 0.78. We notice that they use the same primitives: convolutional neural network and denormalize. We look at their pipeline graphs and we find that they have the same structure. The primitive contribution view shows the correlation between primitives and scores. Convolutional neural network is the primitive that mostly correlates with high scores. Therefore, we are interested in investigating its hyperparameters. We can hover the mouse over the pipeline matrix in order to see the hyperparameter values as a tooltip. However, this does not give us a complete view of the hyperparameter space of the primitive. Instead, we can click on the primitive name in order to expand the matrix with a one-hot encoded representation of the CNN hyperparameters. We can see that the AutoML systems tune hyperparameters for attention, number of epochs, learning rate, and number of cells. The top scoring pipeline did not use attention and had 128 LSTM cells. Let's compare the different strategies the AutoML systems use to create the pipelines. We sort the primitives by type and the pipelines by source. The pipeline matrix provides an overview of how the different systems do the model search. We notice that System A uses the same 2 primitives on most of its pipelines, while the other systems generate pipelines with more diversity. Systems A, B, and C have pipelines with scores greater than 0.7. We can use the pipeline comparison view to see the differences among those pipelines. While systems A and B use the same architecture, consisting of a CNN and a denormalized primitive, System C uses a featurizer, joint mutual information, and k-nearest neighbors to make the predictions. We now investigate the running time of these pipelines. We keep them sorted by their F1 score and switch the metric to time. Systems A and B have better F1 score, but System C produces predictions 10 seconds faster. Looking at the primitive contribution view, we see that CNN is the primitive most correlated with high prediction times. We can export pipelines from systems A, B, and C for further analysis. They are accessible via the Python library. We show a second use case with the diabetes dataset. This time, suppose we are only interested in exploring the pipelines from system E. Since Pipeline Matrix is integrated with Jupyter Notebook, we can easily filter our pipelines using a Python function. In the primitive contribution view, we notice that extra trees is a primitive that correlates with high F1 scores. However, this analysis only considers primitives independently. In our paper, we propose an algorithm to investigate possible combinations of primitives that result in high scores. This algorithm can be accessed in the system via the combinatorial analysis menu. Now, we see that RBF sampler and min-max scalar are primitives that work well together. Thanks for watching.